Hello, my name is WeiQin, and I'll be presenting our work on ITSA and Information-Theoretic approach to automatic shortcut avoidance and domain generalization in stereo matching networks. This work is a collaboration between RMIT University and ECU in Australia. Collecting and generating densely annotated stereo data from the real world can be extremely challenging. This is mainly due to the limitation of LiDAR sensor, such as high price tag and can only generate sparse depth measurements, as well as the limitation of stereo camera system, such as error in calibration, cumbersome post-processing, and synchronization issue during data acquisition. Meanwhile, densely annotated synthetic data can be easily generated using game simulations. Some examples of data generating game simulation are Kala and Cynthia. However, deep stereo matching networks, including the state-of-the-arts that are trained on synthetic data only, fail to generalize to the real-world environment, and their performance drops substantially when evaluated on the realistic target domains. To be practically useful in many applications, a stereo matching model should be able to generalize effortlessly to different domains such as daytime, nighttime, varying seasons, and different weather conditions. In this work, we attempt to unfold an important factor that hinders these stereo matching networks from generalizing across different domains through the lens of shortcut learning. A model is known to suffer from shortcut learning when the model fits a problem using features that are not expected to be relevant to the task, and these features are known as shortcuts. We found that stereo matching networks trained on synthetic stereo data exploit common artifacts from those synthetic data as shortcut for disparity estimation. These shortcuts are local chromaticity feature of the reference viewpoint and consistent local RGB statistics from the stereo viewpoints. As shown in this figure, when the mentioned shortcuts are intentionally removed, the performance of a stereo matching networks, such as PSNet that is trained on synthetic data, drops significantly. To learn only task-relevant information, we turn our attention to the information bottleneck principle, which promotes the learning of compressive yet task-relevant features. However, we found that the simple information bottleneck is insufficient to promote the learning of shortcut invariant features in deep neural networks. The recently proposed robust information bottleneck, which is built upon the information bottleneck principle, encourages the learning of both robust and compressive features. The robust information bottleneck utilizes the statistical feature information to measure the robustness or sensitivity of learned features against perturbation in the input. However, optimizing the feature information requires the computation of second-order derivative. As a result, it is computationally prohibitive for tasks with large dimensional inputs, such as stereo matching. To overcome this problem, we propose an alternative to optimize the feature information, and we call our method ITSA. In general, ITSA consists of two parts: a shortcut perturbation, SCP, and a feature information loss for feature consistency. SCP applies perturbation on input pixels based on the sensitivity measured using the gradient of the feature with respect to the input. Intuitively, pixels with large gradient are likely to include shortcuts as they can have significant impact in changing the extracted features. Then, the feature information loss is employed to promote the learning of consistent features given the original input X and the shortcut perturbed input X star, in the hope that the model will learn to ignore the shortcuts from the input and learn robust features. From the quantitative results included in this figure, we can see that our method can significantly improve the synthetic to realistic domain generalization performance of existing deep stereo matching networks such as PSMNet, GWCNet, and CFNet. For instance, we managed to improve the performance of PSMNet by 25.5% and GWCNet by 7.9% on the KITI 2015 dataset. Our method also able to further improve the performance of existing robust deep stereo matching network, CFNet. In addition, our method can substantially enhance the robustness of deep stereo matching networks that are trained on synthetic data only and outperform fine-tuned models on challenging out-of-domain datasets such as rainy and foggy weathers and nighttime data. Not only that, our method can be easily extended to improve synthetic to realistic domain generalization performance of semantic segmentation tasks. As shown in the table, semantic segmentation network trained with our proposed ITSA method consistently achieve the best performance and outperforms other state-of-the-art approaches. If you're interested in our work, you can find our code using this QR code, and thank you.